The other rule in this section is the quotient rule. So instead of our two functions being multiplied together, now we're going to focus on what would happen if our two functions are divided. So the quotient rule says let f and g be differentiable functions on an interval I where the g of x is not equal to 0. Then f divided by g is differentiable on I, and the derivative with respect to x of f divided by g is this expression, f prime times g minus f times g prime, all divided by g squared. You'll notice that the top looks very similar to the product rule, except that we have a minus instead of a plus. And then the denominator is just the denominator squared. So as long as these two functions are differentiable and we don't get 0 in the denominator, then this thing will work out. That's the quotient rule. Again, it kind of looks like the product rule in the numerator, except we have a minus instead of a plus. And then we have a denominator now, which is g squared. One thing I will say, that the order is very important in this one. So notice how I did the derivative of f times normal g first, and then normal f derivative of g second. I have to make sure I do that because subtraction is not commutative. In other words, if I screwed up the f and g here, I'd mess up my quotient rule. That's not the same case as with the product rule. With the product rule, if I would have rearranged f and g, this is all commutative. So addition is commutative, but subtraction is not. So the product rule, I have a little bit more play with which function I call f and which function I call g. Here, we need to make sure that the f is the numerator and the g is the denominator. Let's do example 4. In example 4, we're trying to find the derivative of the following function using the quotient rule. The function is q of x equals 12 sine x divided by x to the 5th. Let's take the derivative using the quotient rule. So the numerator is 12 sine x. The denominator is x to the 5th. The quotient rule says that if I want to take the derivative of this function, what I have to do is I have to create a fraction. On the top of that fraction, I'm going to have the derivative of the numerator. So that's 12 cosine of x times the normal denominator, x to the 5th, minus the normal numerator times the derivative of the denominator. So 12 cosine x times x to the 5th minus 12 sine x times 5x to the 4th. The denominator has to be my original denominator squared. And that's the quotient rule. I'm going to clean this up so it looks a little bit nicer. I'm going to rewrite q prime of x equals, so 12x to the 5th. A lot of times people will write the 12x to the 5th in front times cosine of x in back, minus, well, if we have 12 times 5, that's 60, so minus 60 x to the 4th multiplied times sine of x, divided by x to the 5th squared is x to the 10th. Now, if you want, you can try to, cancel out, factor out an x to the 4th and cancel that out with some of the like terms in the denominator. But I don't need to do that right now. I think this is as good as I want it to be. So 12x to the 5th times cosine x minus 60x to the 4th sine x divided by x to the 10th. So the quotient rule is applied here. Just like before, when I was looking at the product rule, I didn't prove the product rule always worked, but I did show an example in which algebraic manipulation gave us the same answer as doing the product rule. So in other words, doing algebraic manipulation, then taking our basic derivative rules, gave me the same thing as what the product rule gave me. I'm going to show that again using the quotient rule now. We're going to take h of x equals 12 over x to the 5th, and I'm going to use algebraic manipulation and then take the derivative, and then I will take the derivative using the quotient rule, and I'll show that both are the same. So we'll show that the quotient rule works in this case. Let's start by taking the derivative of h of x equals 12 over x to the 5th using the quotient rule. So we'll begin with the quotient rule. So quotient rule says we're going to take the derivative of the numerator. Derivative of the numerator is derivative of 12. That's a constant number, so that's just 0. Multiplied times the normal denominator minus the normal numerator times the derivative of the denominator. So that becomes 0 times x to the 5th minus 12 times 5x to the 4th divided by the denominator squared. Let's algebraically manipulate this to make this look a little bit nicer. So notice 0 times anything becomes 0. 12 times 5 is 60. So we're getting a negative 60x to the 4th on the top divided by x to the 10th on the bottom. This one you can easily divide. So we go h prime of x is equal to a fraction which has negative 60 on the top and x to the 6th on the bottom. So that's what we get when we do the quotient rule and then simplify. What would happen if we algebraically manipulated this before we took a derivative? Well, it turns out that 12x to the 5th is the same thing as 12 divided by x to the 5th is the same thing as 12 times x to the negative 5th. If I take a derivative of that, I get negative 60 x to the negative 6th power. That's my basic constant times a product, constant times a power rule. So negative 60 x to the negative sixth is my derivative, which we all know that we can rewrite that as negative 60 divided by x to the positive 6. So notice that in each case, I ended up with negative 60 over x to the 6th, regardless of whether I did my basic differentiation rule or whether I utilized the quotient rule. Once again, this does not prove that the quotient rule always works, but it shows you that at least in this case, the quotient rule has to work the way we know it should. So we know it should give us negative 60 over x to the 6th, and lo and behold, it does. That means this example shows that the quotient rule does work. It shows it works in this example, but if you look in your book, you can see that the quotient rule works for any such example. So what I would like you to do is to find the derivative of this function, r of x, utilizing the quotient rule. Go ahead, push pause, and do that, and I will show you how to do it on the next video.